state feedback. Let me just make a case why do control or something, right? So we will have a system x dot equals to ax plus bu. We'll start with LTI and then we'll do the general things, but we'll start with the LTI system. So the question is, let's say, okay, you investigated this system, right? And came out whether it is stable, unstable, whatever it comes out, let's say. Okay. So first of all, stable does not mean it is the best system in the world. Like, let's say I'm this vehicle goes to this point, and that's how what you have a system which goes to origin in some time, right? Whether you want it to go it quickly, more quickly, faster convergence in less time. Okay, so that is not there. So even if system is stable, it may not be the best system in terms of time response or things, right? Or if system comes out to be unstable, then you're also unhappy, right? Or the system comes out to be marginally stable. Whatever is the case, let's say you want to further improve the performance of the system. What else can you do? So you investigated initial stability and every property. What else you can do? So the next question is, okay, can I apply a control and change the system properties? Right? That's what you want to do, right? You want to apply a control that can change the system property, right? You have, so till now you're just understanding the internal dynamics without the input, what happens to the system. And now if you're happy or if you're unhappy or you want to improve the system, you have to use input. And like you take you driving or anything, that's where state feedback is. State feedback is very simple. You are correcting your errors. You're applying control proportional to your errors. Okay. I'm driving and I have to go this side. I'm somehow you have a measurement that okay, I'm this much of this far away from the lane or that lane. You provide that correction. So that's basically state feedback. You're measuring something. You're not applying a feedback to kill that error or make that error zero. So state feedback is basically kind of that portion, that part of it. Okay. So in linear system, your state feedback U. Okay, U is the control input now. Control input. Okay, and it can be scalar, it can be multiple inputs, whatever. Okay, in your quadrotor, you have four inputs, right? Force, thrust, T phi, T theta, T psi, right? You have four inputs. Okay, so basically it will be just K into X. So basically you are applying a linear combination of states as a corrective mechanism to fix your system. Okay, and we will see. We'll take a pendulum example, and then we will take the attitude control of the quadrotor example for. Okay, so now and why I do, so this can be written like this, right? For example, if your U is one, just one and n states, then this K is gain matrix. You call it gain matrix. Okay, so basically you have this system. You have U going in here and you have X coming out. So basically you multiply with minus K these states and then say this is my system, right? So state feedback. So you're taking a feedback, multiply it with minus K and plug it in. Okay. Now what will be K? If it is a single input, it will be just minus K1, K2 up to Kn into your X1, X2, Xn, right? So okay, for a single input, you will need n gains. If it is a single input, you need n gains. So gains can be zero. Like for example, uh, if the first is position, second is velocity, third is acceleration, it may be happen that some of the gains are zero. That means that state feedback is not necessary. But in general, this is a gain metric. But if you have multiple inputs like k for a u1 to uk, then this matrix will be also a matrix like k11, k12 up to k1, k1n up to k1 to kkn into your x1 to xn. Okay, so basically each input then is a linear combination of these states, right? Each input is a linear combination of your states. So each row of this gain matrix basically multiplied by this state gives you the input. Okay, so this is what state feedback is, and we will use this to make our system do whatever we want that system to do. Going to a point, tracking a trajectory, okay, our quad rotor flying figure eight, tracking the attitude or hover at a particular position, whatever that is. We will use this type of input. So what is left then? You would say this should be that simple, right? U equals to minus kx. The question is, how do you select these things, right? What is the criteria to select these gains? How do you select them? There are so many criterias, right? First criteria, okay. So now the whole next of the couple of lectures will be just coming up with this gain K matrix, and because otherwise it's from implementation perspective it is very simple. Just give these u equals to minus kx. That's one term. It computes everything. Okay. So now the focus should be how should we select gain K. Okay. There are different ways. So first of all, let's see how it affects the system. What I'm talking like how is it changing something, right? So let's see x dot equals to ax plus bu, right? Now let's say I'm forget see for now I'm just worried about this that if I can take my states to desired states means I can take my system to desired output also. So you can track outputs, you can track states, whatever you want. So if I plug in u equals to minus kx, what happens to this? Ax plus minus bkx, and then it becomes x dot equals to a minus bkx. Okay. Now what can you say? Let's say your internal your system A matrix has some positive eigenvalues. Let's say, right? So that means system is unstable. The original system is unstable. But now I have applied state feedback. Means this additional term bk has come, right? Minus bk. I'll take an example how it affects, but minus bk has come, right? Like now b is fixed, but k is my choice. I can choose k to make this system stable. Right? That's one control input. So let's take an example if we can just cook example. Let's say x dot equals to 1 0 0 minus 2 into x plus 0 1 into u. That's my system. Okay. What are the eigenvalues here? Is this original system unstable? Yes, right? The eigenvalue of A are 1 and minus 2. So your system is unstable. Let's apply controller now. Okay, so let's apply u equals to minus kx, where k is, let's say, k1 and k2. There are two gains for each state, right? x1 and x2. What happens when I apply there? Let's apply. So x dot equals to 1 0 0 minus 2 into x minus 0 1 into k1 k2 into x also, right? This is x. So now this can be written as, I'm just motivating this example, 0 minus 2. So x can go out. This is bk, 0 1 k1 k2 into x. And so this is a, this is bk, right? So it can be written as 1 0 0 minus 2, and it becomes 0, 0, k1, k2 into x, right? So now let's see. 1, 0 minus k1 minus 2 k2. Oh, sorry, minus 2 minus k2 into x. Okay. So now this is my A minus BK into X matrix, right? So I haven't chosen K1 and K2 yet, right? So my the initial matrix was unstable. Now I want to make it stable. That's all I want right now. So let's say, what are the eigenvalues? How do I compute eigenvalues? The eigenvalues are no longer just 1 and minus 2, right? So it will be S or lambda I minus A, which will be equal to 0, determinant of this, right? That's how I will compute eigenvalues, and that comes out to be lambda minus 1, 0, k1, lambda plus 2 plus k2, uh, right? And so determinant of this will be what? Lambda minus 1 into lambda plus 2 plus k2 equals to 0. Is that correct? I think I didn't choose a good example here because 1 lambda still comes out to be 1, right? So that also brings you to the another question which we theoretically will uh, do later, is whether you have enough control power to change poles or not. So that's the concept of controllability. Here, there is no matter what I do, I cannot change this pole here, right? So that means system is uncontrollable. Okay. So we will come to that. Yes. We'll take, yeah, we'll take 1 1 or something. Let's see if I can do 1 1. Uh, so 1 1 will do what? K1 K2 both sides here, and K1 K2, and that will give me minus K1 and minus K2, right? And then, so this time it should be okay, right? So that's my A minus BK. So now I want to do lambda minus 1 minus K1, right? 1 minus K1. Okay, 1 minus K1 minus K2 minus K. So that's correct. So that means it will be 1 minus plus K1, right? Everything else is okay? And this will also come here, K2. So now it is lambda minus 1 plus K1. I should have chosen a better example, but this also, like, there are a lot of interesting points coming here. Whether your matrix is in good form or right. You remember I said if your matrix is in controllable canonical form, it is easier to choose these gains. So you first have to do some transformation to make this A matrix looking good, where this operation becomes simpler, and also the controllability aspect. So you already kind of are motivated for those two interesting things that are coming later, whether my system is controllable as well as is it in good form to do this hand computations, or should I use MATLAB? Uh, and this will be into lambda plus 2 plus k2 minus k1 k2, right? Anyways, the now lambda 1 and lambda 2, when you solve for it, it should be function of k1 and k2, and I will be able to pick K1 and K2 such that the real parts of the eigenvalues are in the left half of S plane. And then we are done. So what happened there? Originally unstable system, I closed the loop, I did a state feedback, and I'm able to make it. So let me take a good example. I'm not much, but we only have 3 minutes, so I better be quick. Okay, just to motivate, let's show you a simulation, right? Like that's a better thing to do. So, so this will be our, so the next couple of, maybe next whole 1 month, we'll be talking about this selection of K1 and K2 and then using them to examples. Okay. So let's see, we have some examples somewhere, OneDrive, teaching, MATLAB, inverted pendulum. So do you remember your inverted pendulum example that we were doing? Huh? Okay. Uh, oh man, Jesus. So if you remember your pendulum example, I think there were what, two states, right? Theta, theta dot, and and I think it was four states for pendulum on the cart. So if you had this, oh, I'm where I'm drawing, but so two states of your cart and two states of your pendulum, and if you do the eigenvalue analysis, the pendulum will be unstable. At least the top part, you leave it, it will drop. Okay, so at least at the equilibrium point that I am want to keep it. So if I want to keep the pendulum straight, at that equilibrium point, your eigenvalues of that system are not going to be all negative, right? So what I did here was the state feedback. So there are different ways of choosing gains that will come. One will be LQR, one will be pole placement, things like that. So in this case, I'm using pole placement, but it is basically U equals to minus KX going in. So I have four states, one input. Okay, so I'm using one. Okay, so the objective is to go to zero. Okay, and zero this time I have defined that is this vertical point, right? So let's see if I can open that file for you. Okay, so actual system is nonlinear, but I can do some small angle approximation to get A and C, A, B, and C, right? Or you can linearize it around that equilibrium. So any way, any method should work. Remember, I'm only using approximations to do what? Compute my controls. I'm not making any approximation on my plant. Plant is still nonlinear. Okay, you need to remember that. So that will be cheating if your plant is also linear and this is all like that will be not good. Okay, so basically this method you right now you don't know this method, but basically I compute a gain K matrix K here, K, right? Somehow magically I computed this gain K, which makes my poles or eigenvalues at a point where, let's say I want the good thing is you can actually choose your eigenvalues. So let's say it was 1 and minus 2, right? Initially, I can say I want my eigenvalues to be at minus zero point 0.5 and minus zero point 0.5. and you will get a gain matrix for that. If your system is controllable, you will get an exact unique gain matrix, which will, if you use that u equals to minus kx, your closed loop eigenvalues will be minus zero point 0.5, minus zero point 0.5, depending on what that gain. So yes, if your system is controllable, oh, sorry, if your system is controllable, you can exactly place your eigenvalues wherever you want. Okay, so question, if controllable, you can place your eigenvalues using the state feedback anywhere you want. So you will get some k1 and k2. For example, let's say this, I got this k, right? We'll go over this whole process in the next class or so. And that same thing we will apply for the attitude control of the quadrotor. So if I make this k to be 0, right? For example, right now, let's make it 0. So control as, that means there is no control. And let me run this system. Hopefully it runs. Jeez. Anyways, its time is also over. So